In the heart of the Industrial Revolution, towering steel vessels roared like man-made volcanoes. When the air blast began inside a Bessemer process converter, flames erupted skyward, and molten metal churned with barely restrained violence. To investors, it was progress forged in fire. To the men standing on the casting floor, it was something far more unpredictable. These converters built railways, warships, and skyscrapers, but they also hid defects, sparked deadly eruptions, and ignited battles over safety and accountability. Behind the spectacle of industrial triumph lay a volatile truth. Sometimes the volcano didn't stay contained. This is the story of the deadliest Bessemer converters ever built, and the consequences when industrial ambition outpaced control. Fire without control. Why early Bessemer converters were inherently dangerous. In the mid-19th century, steel was expensive, slow to produce, and strategically vital. Railways, bridges, artillery, and shipbuilding all depended on stronger, more reliable metal than traditional wrought iron could provide. When the Bessemer process was introduced, it promised something revolutionary: mass-produced steel at unprecedented speed. What it also introduced, less advertised but equally real, was a system of controlled chemical violence operating at the edge of human understanding. At the center of the process stood the Bessemer converter itself, a massive, pear-shaped steel vessel lined with refractory material and mounted on trunnions so it could tilt. Molten pig iron was poured into its belly, and then air was blasted upward through tuyeres in the base. That air was not merely cooling or stirring the metal, it triggered an intense oxidation reaction. Silicon, carbon, and other impurities burned inside the liquid iron, generating extreme heat. Flames shot from the converter's mouth, sometimes dozens of feet into the air, creating a spectacle that earned the nickname Volcano. The danger was not incidental to the process, it was fundamental to it. Unlike later steelmaking systems equipped with refined temperature monitoring and chemical analysis, early Bessemer operations relied heavily on visual judgment. Skilled workers watched the flame color and intensity to determine when the carbon content had dropped to the desired level. The entire reaction unfolded in minutes, not hours, leaving little margin for hesitation. If the blow continued too long, the steel could be ruined. If it stopped too early, impurities remained. Inside the vessel, temperatures soared beyond 1,600 degrees Celsius, and the reaction could shift violently with small variations in composition. The converter's scale amplified the risk. Early adopters quickly realized that larger vessels meant greater output and lower per-ton costs. Industrial competition encouraged scale before safety systems matured. Enlarged converters held more molten metal, which meant that any instability involved exponentially greater thermal mass. A minor refractory lining failure could expose the steel shell beneath to direct contact with molten contents, weakening structural integrity in seconds. When that happened, rupture was not theoretical, it was catastrophic. Air pressure presented another hazard. The blast required to oxidize impurities had to be forceful enough to agitate tons of molten iron. Excessive pressure, however, could produce violent splashing, or what operators referred to as boiling eruptions. Slag and metal could surge upward, escaping the mouth of the converter and showering the surrounding floor with incandescent droplets. Workers stationed nearby to monitor the blow had little physical protection beyond basic clothing and distance. Refractory linings were a persistent vulnerability. The interior of the converter was coated with materials designed to withstand extreme heat and chemical attack. Yet, early refractory science was imperfect. Linings degraded unpredictably, especially when processing iron with high phosphorus content. As erosion advanced, weak points developed. A lining breach during a blow could allow molten metal to infiltrate cracks, expand under heat, and fracture the vessel. In extreme cases, structural failure led to explosive releases of superheated metal. The inherent volatility of the process also stemmed from its chemistry. The oxidation of silicon and carbon released immense energy, and that energy was not externally regulated. Unlike furnaces heated gradually from outside, the Bessemer reaction intensified from within the metal itself. This internal combustion created self-accelerating dynamics. If impurity levels were higher than anticipated, the reaction could spike rapidly, overwhelming expectations based on previous heats. Operators often lacked precise pre-blow chemical analysis, making each batch a calculated risk. Environmental conditions compounded instability. Moisture entering the system, whether from damp linings or ambient exposure, could vaporize explosively upon contact with molten metal. Steam expansion inside confined channels increased pressure unpredictably. In an era before comprehensive industrial standards, maintenance routines varied widely between plants, and the absence of uniform safeguards meant that practices depended heavily on local management priorities. Economic pressure intensified these structural dangers. Steel demand was soaring, and downtime translated directly into financial loss. Shutting down a converter for inspection or relining was expensive and time-consuming. Some facilities pushed equipment beyond safe operating intervals to meet contracts, accepting elevated risk as a cost of competitiveness. The converter's dramatic efficiency encouraged a culture of acceleration, where throughput overshadowed precaution. The visual drama of the volcano often obscured the underlying fragility of control. Spectators saw towering flames and assumed mastery over elemental forces. In reality, early operators were managing a narrow window between productive reaction and uncontrolled release. The Bessemer converter was revolutionary precisely because it harnessed violent chemistry for industrial gain, yet that same violence ensured that every heat carried latent instability. Fire was not merely contained within iron walls, it was unleashed deliberately and redirected. The technology succeeded because it embraced that intensity, but it remained inherently dangerous because full control lagged behind ambition. In its early decades, the converter embodied a paradox of industrial progress. The faster steel could be made, the more precarious the margin between innovation and disaster became. The volcano effect, when molten steel erupted without warning. Inside a working Bessemer shop, there was a moment every crew recognized: the shift in sound. At first, the converter's blow produced a steady roar as air forced its way through molten pig iron, igniting silicon and carbon in a violent oxidation reaction. Flames climbed from the mouth in controlled fury, a predictable plume that experienced operators read like a barometer. Then, sometimes without clear warning, the rhythm changed. The roar sharpened, the flame thickened, and the surface inside the vessel began to churn in a way that signaled instability rather than routine combustion. The process, by design, invited volatility. The Bessemer process relied on forcing air upward through tuyeres embedded in the base of a pear-shaped converter filled with several tons of molten iron. As impurities oxidized, enormous heat was released internally, driving temperatures to extremes without external fuel. The reaction was not gradual, it unfolded in minutes. When chemical balance aligned with expectations, the blow followed a recognizable arc. When it did not, the converter became something far closer to its nickname, a volcano. Eruptions were not metaphorical exaggerations. Under certain conditions, slag and molten metal could surge violently upward and spill over the lip of the vessel. Operators referred to these incidents as slopping or boilovers, but the terminology softened the reality. A converter mouth positioned several meters above the casting floor could disgorge incandescent metal in arcs that scattered unpredictably. Droplets cooled mid-air into razor-edged fragments, while heavier masses struck the floor in splashes that ignited secondary fires. Several factors made these eruptions difficult to anticipate. Variation in the chemical composition of pig iron was one persistent cause. Early steelworks did not benefit from the rapid, precise spectrographic analysis available to modern metallurgy. Impurity levels, particularly silicon, manganese, and phosphorus, could differ between batches. Because the oxidation of these elements generated heat at different intensities, an unexpectedly high concentration could accelerate the reaction beyond the operator's visual cues. The converter's interior was another variable. Refractory linings eroded unevenly over time, especially when subjected to repeated thermal cycling. Thin spots could alter airflow distribution from the tuyeres, creating localized turbulence inside the molten bath. Instead of a uniform agitation, the interior might develop pockets of concentrated reaction where gas expansion forced metal upward in violent bursts. By the time surface behavior signaled trouble, momentum was already building from below. Air pressure settings compounded the risk. Blast rates were adjusted to optimize impurity removal, yet small miscalculations could destabilize the surface of the melt. Excessive airflow increased agitation, raising the likelihood that gas bubbles would coalesce into larger, forceful expulsions. In effect, the converter could behave like a sealed chamber accumulating pressure, even though it was technically open at the top. The visible flame was not merely decorative. It was the exhaust of a rapid chemical storm occurring beneath. The physical layout of early steel plants intensified vulnerability. Workers stood near the converter during the blow to monitor flame color and intensity, because visual assessment was the primary control instrument. There were no remote sensors, no protective barriers beyond distance and instinct. When eruptions occurred, proximity translated directly into injury. Burns, blindness from intense light exposure, and impact trauma from flying debris were documented consequences in multiple facilities during the process's early decades. Competition within the steel industry discouraged extended caution. Production quotas were rising, and downtime for inspection or relining reduced output. If a converter showed signs of instability but continued to produce saleable steel, management faced pressure to maintain operations. In such an environment, warning signs could be interpreted as manageable anomalies rather than systemic risks. The volcano effect thus became normalized as an occasional hazard rather than a design vulnerability. Environmental conditions introduced further unpredictability. Moisture, trapped in scrap additions or residual dampness in linings, could vaporize instantly when exposed to molten metal. Steam expansion amplified internal turbulence, sometimes triggering explosive splashes. These incidents blurred the line between chemical reaction and physical shock, reinforcing the sense that the converter was balancing on a narrow threshold of stability. Observers, unfamiliar with the process, often perceived the towering flames and showers of sparks as theatrical proof of industrial mastery. In truth, the spectacle masked a precarious equilibrium. The Bessemer converter harnessed uncontrolled chemical energy and redirected it toward productive ends. But the control mechanisms were largely experiential rather than mechanical. When judgment faltered or variables aligned unfavorably, the system reverted to its elemental nature. The volcano was therefore not an aberration. It was an inherent expression of the forces at work inside the vessel. Molten steel did not erupt because operators were careless in every case, nor solely because equipment failed. It erupted because the process demanded the rapid release of energy on a scale that outpaced the precision of 19th century monitoring. In those moments, the boundary between industrial innovation and raw thermodynamic chaos narrowed to a margin measured in seconds. The race for bigger furnaces, scaling up beyond safety limits. In the decades after the introduction of the Bessemer process, the steel industry entered a period defined by acceleration. Railroads were expanding across continents, naval fleets demanded stronger hulls, and urban skylines began reaching upward with iron-framed ambition. Steel was no longer a specialty material. It was the backbone of industrial modernity. Under such demand, the logic seemed obvious. If a converter could produce several tons of steel in minutes, then a larger converter could produce even more. Output became the central metric of success, and scale was the pathway to dominance. Early Bessemer converters already operated at extreme temperatures and chemical intensities, but competitive pressure encouraged manufacturers to increase vessel capacity. Enlarging the converter meant thicker shells, more refractory lining, and greater volumes of molten metal reacting simultaneously. On paper, the mathematics were compelling. Higher capacity reduced the number of heats required to meet contracts, lowering labor costs per ton. Investors and plant owners viewed expansion as evidence of progress, equating size with efficiency. What expansion also introduced was exponential risk. The internal reaction within a converter is self-heating. Oxidation of impurities releases enormous thermal energy. When vessel volume doubled, the potential energy of a single blow increased dramatically. More molten metal meant more oxidizable material and more gas evolution. A miscalculation in chemistry or air pressure did not scale linearly. It amplified. Structural tolerances that were marginally acceptable in smaller converters became dangerously thin margins in oversized ones. Engineering knowledge struggled to keep pace with ambition. Metallurgical science was advancing, but predictive modeling of stress distribution under extreme heat was still rudimentary. Large converters experienced uneven thermal expansion across their shells and linings. Even minor inconsistencies in refractory thickness could produce stress concentrations. When the interior temperature spiked during a blow, the outer steel shell had to endure intense internal pressure combined with expansion forces that were not evenly distributed. Failures in larger furnaces were correspondingly more destructive. A lining breach in a small converter might release a limited stream of molten metal before operators could tilt and dump the contents. In a high-capacity vessel, a breach could trigger catastrophic rupture. Tons of liquid steel escaping at over 1,500 degrees Celsius did not merely spill, they surged outward, igniting flooring materials and engulfing equipment. The scale of destruction increased alongside production metrics. Air delivery systems also faced new strain. To agitate larger volumes of molten iron effectively, blast pressures had to be increased or airflow distributed through more tuyères. Both adjustments introduced complexity. Higher pressure intensified turbulence inside the melt, raising the likelihood of violent surface eruptions. Expanding the number of tuyères created more potential points of failure in the base of the converter, where erosion was already a persistent problem. Maintenance became more demanding, yet shutdowns were financially painful. Industrial rivalry magnified these vulnerabilities. Steel magnates in Britain, the United States, and continental Europe competed openly on output figures. Public claims about daily tonnage and converter size became markers of prestige. Investors interpreted expansion as a sign of strength, reinforcing incentives to push equipment beyond conservative operating limits. In some facilities, scaling decisions were driven more by market positioning than by cautious engineering review. Workers bore the consequences of these choices. Larger converters required crews to operate in closer coordination around heavier tilting mechanisms and wider casting pits. The physical footprint of the operation expanded, but protective infrastructure did not always expand proportionally. Platforms, shielding, and escape routes were often retrofitted rather than redesigned from first principles. When incidents occurred, the increased mass of molten material meant that reaction time was minimal and survivability diminished. Environmental strain accompanied mechanical stress. Larger furnaces consumed greater quantities of pig iron and air, generating thicker plumes of exhaust gases and more intense radiant heat. Ventilation systems were frequently inadequate for the scale of operations, exposing workers to higher concentrations of fumes and sustained heat stress. The push for volume inadvertently intensified occupational hazards beyond immediate catastrophic events. Not all scaling efforts ended in disaster, and many large converters operated successfully for years. However, the pattern of incidents in rapidly expanding plants revealed a consistent theme. Growth outpaced standardization of safety practices. Lessons learned from smaller-scale failures were not always integrated before expansion proceeded. Economic optimism created a bias toward innovation over restraint. The race for bigger furnaces therefore became more than a technological progression. It was a contest between ambition and prudence. As steel output climbed, so too did the magnitude of potential failure. The converter, already a controlled chemical eruption, became an even more formidable vessel when enlarged. Scaling up did not merely increase productivity, it magnified every underlying vulnerability, transforming manageable hazards into systemic threats whenever calculation fell short of reality. Death on the casting floor, the human cost of industrial speed. In the age of expanding railways and rising steel bridges, production figures were celebrated as proof of progress. Weekly tonnage became a point of pride for industrialists, and the success of the Bessemer process was measured in how quickly molten iron could be transformed into usable steel. Yet, beneath the statistics and investor reports, the casting floor told a different story, one written in burns, crushed limbs, and lives cut short by the relentless tempo of industrial speed. The Bessemer converter operated in dramatic cycles. Once the blow was complete and impurities oxidized, the vessel was tilted to pour the newly formed steel into ladles. Timing was critical. The metal could not be allowed to cool prematurely, nor could it be mishandled during transfer. Crews positioned around the converter coordinated the tilt, monitored flow, and prepared molds or secondary furnaces. Each movement unfolded in proximity to tons of liquid metal heated beyond 1,500 degrees Celsius. There was no gradual margin between safe and fatal exposure. The boundary was measured in seconds and centimeters. Industrial speed amplified this danger. Demand for steel incentivized rapid turnaround between heats. Once one blow concluded, the next charge of pig iron was already being prepared. Extended pauses for equipment inspection or crew rest were seen as inefficiencies. Workers were expected to maintain alertness through consecutive cycles, even though fatigue dulled reflexes and judgment. In an environment where a single misstep could result in catastrophic injury, exhaustion became an invisible hazard layered atop visible ones. Protective equipment in early steelworks was rudimentary. Heavy boots and basic clothing offered limited resistance against splashes of molten slag. Eye protection, when used, was often inadequate against the intense glare emitted during a blow. The casting floor was a terrain of uneven surfaces, rails for moving ladles, and machinery whose scale dwarfed human operators. Navigating this space required experience and coordination, yet turnover rates in some plants were high due to injury and burnout, meaning that not every worker had the benefit of long apprenticeship. Accidents occurred in multiple forms. A misaligned ladle could tip unexpectedly, sending a stream of molten steel across the floor. Slag crusts that appeared solid might conceal liquid beneath, collapsing under a worker's weight. Mechanical failures in tilting mechanisms could shift the converter's balance abruptly. Even routine tasks such as clearing debris posed risks, as residual heat lingered long after visible flames subsided. Each incident underscored how little separated routine operation from disaster. The economic structure of the industry often complicated responses to injury. Compensation systems were inconsistent, and in some regions, minimal. Injured workers might receive limited support, while families of the deceased faced financial uncertainty. The speed that made steel profitable did not necessarily translate into comprehensive safeguards for those who sustained the process. In certain cases, plants resumed operations swiftly after fatal incidents, prioritizing contractual obligations over thorough investigation. Labor unrest grew in part from these conditions. As unions gained traction in industrial centers, worker advocates began highlighting the frequency of injuries and the lack of standardized safety measures. Demands for improved protective gear, regulated shifts, and clearer emergency protocols clashed with management's emphasis on output. The casting floor thus became not only a site of physical hazard, but also a focal point of industrial conflict between labor rights and production targets. Environmental stress further strained workers. Radiant heat from converters and ladles elevated ambient temperatures well beyond comfort, especially during summer months. Ventilation systems struggled to disperse fumes, and metallic dust generated during pouring and skimming. Prolonged exposure to such conditions contributed to chronic health issues, compounding the immediate dangers of burns and trauma. Industrial speed did not allow for slow adaptation. It required bodies to endure extremes repeatedly. The narrative of technological triumph often centered on innovation and economic expansion, yet it obscured the human calculus underpinning those achievements. Each ton of steel represented coordinated effort under hazardous conditions. The converter's efficiency compressed time, but it also compressed reaction windows for workers operating in its shadow. The faster steel flowed, the narrower the margin for error became. On the casting floor, progress was tangible and unforgiving. The glow of molten metal illuminated both the promise of modern industry and the cost borne by those closest to the heat. Industrial speed transformed steelmaking into a cornerstone of development, but it also ensured that the human price was paid not in abstract figures, but in immediate and often irreversible consequence. Hidden defects and corporate silence cover-ups in the Steel Age. By the late 19th century, steel had become synonymous with national strength. Railroads stitched continents together. Skyscrapers redefined city skylines, and naval fleets projected industrial power across oceans. At the center of this transformation stood the Bessemer process, a technology that made high-volume steel production economically viable. Yet, beneath the narrative of progress, another pattern emerged, one less publicized and far more contentious: the management of failure. Industrial accidents were not rare in early steelworks. Converter eruptions, ladle spills, refractory collapses, and structural fatigue incidents occurred with unsettling regularity, particularly in facilities that pushed production limits. What distinguished some plants was not merely the frequency of these events, but how they were reported or not reported. Documentation standards varied widely, and in many cases internal logs remained confined to company archives, inaccessible to workers, regulators, or the public. The absence of comprehensive industrial regulation created space for discretion. Plant managers controlled incident records and determined whether events were classified as minor disruptions or serious safety breaches. Fatalities might be described in internal correspondence as unfortunate but unavoidable, while systemic equipment defects were attributed to operator error rather than design flaws. This framing protected corporate reputation at a time when investor confidence was closely tied to perceived operational stability. Converter linings and structural shells presented a recurring source of concealed vulnerability. Refractory erosion could advance unevenly, weakening vessels in ways not immediately visible from the exterior. In some facilities, recommendations for early relining were postponed to avoid costly downtime. Engineers who raised concerns sometimes encountered resistance, particularly when repairs threatened production quotas. The calculus was pragmatic. Temporary risk might be tolerated if output targets were met, and no public incident forced scrutiny. Insurance investigations occasionally revealed deeper tensions. When catastrophic failures occurred, such as converter ruptures that released tons of molten steel, external assessors examined maintenance practices and equipment histories. Discrepancies between official statements and documented wear patterns sometimes surfaced, suggesting that warning signs had preceded the event. However, settlements were frequently negotiated privately, limiting the dissemination of findings that might have triggered broader industry reforms. Labor organizations played a crucial role in challenging this culture of silence. As union representation expanded in industrial centers, workers began to share accounts of near misses and suppressed complaints. Testimonies described instances in which management discouraged formal reporting of injuries to avoid attracting regulatory attention. In environments where employment was precarious, workers faced implicit pressure to accept hazardous conditions rather than risk dismissal. Public perception of steel magnates further complicated the issue. Prominent industrialists were often celebrated as architects of economic growth, philanthropy, and technological advancement. Criticism of their operations could be portrayed as resistance to progress itself. Newspapers dependent on advertising revenue from major industrial firms were not always inclined to pursue investigative reporting on plant-level safety controversies. As a result, systemic hazards could persist without sustained external challenge. Technical ambiguity also facilitated corporate defensiveness. The Bessemer process was inherently volatile, and not every incident stemmed from negligence. Differentiating between unavoidable risk and preventable defect required expertise that was still developing. Companies could plausibly argue that certain accidents reflected the unpredictable nature of high-temperature metallurgy rather than managerial oversight. This ambiguity created space for interpretation that favored continuity over reform. Gradually, patterns of injury and structural failure became more difficult to dismiss as isolated events. Industrializing nations began considering standardized safety codes. insurance reforms, and reporting requirements. Engineering societies published papers analyzing converter wear and advocating for improved refractory materials and inspection protocols. Transparency did not emerge overnight, but incremental regulatory pressure narrowed the latitude for concealment. The era of hidden defects and corporate silence reveals a recurring tension within rapid industrialization. Technological breakthroughs accelerated production, yet governance mechanisms lagged behind. When profit margins depended on uninterrupted operation, acknowledging systemic flaws carried financial and reputational costs. In such circumstances, silence could appear expedient. Ultimately, the steel age was not shaped solely by innovation, but also by the struggle to align industrial ambition with accountability. The converter's fire illuminated both economic progress and institutional shortcomings. As scrutiny intensified and labor advocacy gained momentum, the space for undisclosed risk diminished, reshaping how heavy industry confronted its own vulnerabilities. When the volcano backfired, explosions, shutdowns, and forced reforms. For decades, the Bessemer converter symbolized industrial momentum. Its towering flame and thunderous blow became visual shorthand for modern steelmaking, a spectacle that suggested mastery over chemistry and heat. Yet the same forces that made the Bessemer process revolutionary also ensured that when control faltered, the consequences were immediate and devastating. The volcano did not always obey its operators, and when it backfired, entire plants could be thrown into crisis. Explosions in Bessemer shops rarely resembled cinematic fireballs. They were more often violent structural failures triggered by internal instability. A refractory lining weakened beyond tolerance might give way during a blow, allowing molten metal to breach the vessel's interior wall. Contact between superheated steel and cooler structural elements could generate rapid expansion and fracturing. If air continued to blast through compromised tuyères, pressure dynamics worsened, transforming a breach into a rupture. When a converter shell split under those conditions, tons of incandescent metal escaped in seconds. Such events did not merely injure workers, they halted production instantly. Casting floors were left scorched and obstructed by solidified steel. Cranes and ladles were damaged or rendered unusable. Cleanup required cooling, cutting, and removing hardened masses that sometimes fused to structural supports. In facilities operating on tight schedules, a catastrophic converter failure could suspend output for weeks, undermining contracts and eroding market confidence. Beyond immediate physical damage, explosions exposed systemic weaknesses that management could no longer downplay. Insurance assessors, local authorities, and sometimes government inspectors scrutinized plant practices with renewed intensity. Questions emerged about inspection intervals, refractory quality, air pressure regulation, and worker training. Documentation that once remained internal became evidence in disputes over liability and compensation. Public reaction intensified when fatalities accompanied structural failure. Industrial accidents were not uncommon in the 19th and early 20th centuries, but large-scale explosions drew broader attention because they were visible, disruptive, and difficult to attribute solely to operator error. Newspapers reported on converter ruptures that shattered windows and sent plumes of smoke above industrial districts. Community awareness transformed private factory incidents into public controversies. Shutdowns, triggered by major failures, forced companies to confront the financial trade-offs they had long balanced informally. Temporary closure meant lost revenue, contractual penalties, and reputational damage. Yet, reopening without substantive changes risked recurrence and deeper scrutiny. Some plants invested in improved refractory materials, redesigned tuyères, and more rigorous inspection schedules as a condition for resuming operations. Others faced regulatory mandates that formalized safety practices previously left to managerial discretion. The competitive landscape of steelmaking also shifted in response to high-profile converter disasters. Alternative processes, particularly open hearth furnaces, gained credibility because they offered slower but more controllable production cycles. While less dramatic in operation, open hearth systems allowed for greater adjustment during the melt, reducing the likelihood of sudden violent reactions. As industrial buyers prioritized reliability alongside cost, the appeal of a less volatile process increased. Reform did not occur uniformly or immediately. Resistance persisted in facilities where profit margins were thin and capital for upgrades scarce. However, the cumulative effect of repeated converter failures gradually narrowed tolerance for risk. Engineering societies published analyses emphasizing preventative maintenance and structural reinforcement. Insurance premiums began to reflect safety records, creating economic incentives for compliance. In some jurisdictions, government authorities codified reporting requirements and inspection standards. Workers and labor organizations leveraged the visibility of catastrophic events to press for broader protections. Demands for clearer evacuation protocols, improved protective equipment, and regulated shift lengths gained traction in the aftermath of explosions. Where earlier complaints might have been dismissed as routine hazards of heavy industry, large-scale shutdowns reframed safety as a structural issue rather than an individual failing. The backfiring of the Volcano thus reshaped industrial steelmaking in ways incremental caution had not achieved. Spectacular failures exposed the fragility beneath apparent control, compelling companies to reconcile ambition with sustainability. The converter remained a powerful tool, but its operation increasingly incorporated lessons paid for in damage and disruption. In the arc of industrial history, reform often follows rupture. When Bessemer converters exploded and production lines fell silent, the interruption forced reflection that routine operation discouraged. Out of those moments emerged a more regulated, technically refined steel industry, one that acknowledged, however reluctantly, that harnessing fire at industrial scale demanded more than confidence and speed.